welcome back to the course. In the last class we began looking at 2D NOESY, which stands for 2D nuclear Overhauser spectroscopy. This along with another experiment called ROSY is a very set of very important experiments in NMR, especially biomolecular NMR for protein structure determination. So, we will dwell some more time on these two experiments and understand them thoroughly before we actually start using them when down the line when we solve the structures. So, let us look at just the NOE effect first. What is nuclear Overhauser effect? This effect was historically discovered actually in metals, not in nucleus or not in solution or not in molecules, but the idea was that there is a dipolar interaction between electrons and metals, and that was resulting in some kind of a magnetization transfer, and the same thing is what is exploited now in molecules. So, basically the idea is the following. Any spin in NMR, any NMR active spin such as hydrogen or carbon 13, they are actually small tiny magnets. This is something which we saw in the very beginning of the course. This magnetic, they have what is called as magnetic dipole. So, when you have two dipoles close to each other such as two hydrogens or two carbons, what happens is these two dipoles start interacting with each other, and that is called dipole-dipole interaction. And this is an interaction which is something which happens between any two magnetic dipoles. It can happen between proton and carbon, it can also happen between carbon and carbon, but by far proton to proton is the strongest dipolar coupling, because this dipolar coupling depends on the gyromagnetic ratio of the nucleus involved. So, gyromagnetic ratio of proton being the highest in the NMR, the two protons which interact will have the highest dipolar coupling. So, what do we do in nuclear Overhauser effect or in spectroscopy, or what is NOE? So, suppose let us say I take this molecule which is a very simple linear chain molecule, and I irradiate, means I apply an RF energy, this RF energy, it can be a pulse, it can be a continuous RF increasing energy and so on, but if I apply it on a particular hydrogen, let us say I choose this methyl proton. This methyl proton, now this is perturbed, meaning it is excited or it is perturbed from its equilibrium state, and that information now is actually starts getting transmitted to this proton. In other words, when this proton starts relaxing back to its original equilibrium position, this starts affecting the relaxation of this nucleus as well. So, these two hydrogens, this hydrogen now which is close to this hydrogen gets affected because this hydrogen is irradiated, okay. And if I irradiate this hydrogen, it can affect this hydrogen or it can affect this hydrogen as well. So, the important point here in NOE is that there is a distance or a proximity dependence or vicinity. Hydrogens which are close to each other in space are the ones which are affected by each other. So, here we do not consider J coupling, this phenomenon is purely through space effect, meaning it is in the three dimensional space. In this small molecule, of course, they are all close to each other, but if you consider a biomolecule such as protein, it has much longer chain. It consists of amino acids, as we will see later in the course, and there are many amino acids joined together linearly, and the protein starts folding, meaning it curls up and it forms a specific three dimensional structure. And that now it depends, now what happens is two hydrogens. So, let me show you this schematically now. So, if I have a protein which is a chain which goes like something like this, and it can come close back and it can form kind of a close or loop structure, or this is a three dimensional structure approximately of a protein. So, if I have two hydrogens, suppose I have an hydrogen here, proton A, and I have another hydrogen B, let me call it proton B. Now, these two are now coming very close in space, this could be less than 5 angstrom. We will look at this distance concept little bit later, but let us say these two hydrogens are very close in space. So, what you can see here that bond wise, if you go through this entire chain, they are really far away, it could be 200 bonds, 300 bonds and so on, but when it comes to being close in space, they are very close to each other. So, now if I irradiate this hydrogen by RF frequencies similar to what I showed here, this irradiation is transmitted to this proton. So, the magnetization or the energy of this hydrogen or the population of this hydrogen is affected because of the perturbation of the population of the other hydrogen H A. So, now this information, this perturbation of B because of A is happening only because of this dipole interaction which happens through space. So, you see it is very useful to do NOE because it immediately gives us an idea about what is the effect of distance on the magnetization. So, this is basically a very useful experiment to be carried out in general for structure determination of biomolecules. So, now you can see here this is a schematic again for the same this. So, you can see here the arrow is slightly displaced, but this irradiation of this methyl proton affects the methylene proton here, and not only methylene proton, it also will affect this methylene proton here. Why is this? Is because these two also are not very far away. These two hydrogens are also pretty close by, they are within 5 angstroms. So, anything which is within this 5 to 6 angstrom is basically affected when the protons are irradiated. So, this brings us essentially to this concept of distance which I was talking about. So, now you can see here if two hydrogens are within the radius of 5 to 6 angstroms, they are affected by irradiation of nearby proton. So, essentially if I irradiate this hydrogen will be affected, and if I irradiate this hydrogen will be affected. Now, why is this concept of 5 to 6 angstrom, from where is it coming from? This limit that we cannot observe irradiation or affect irradiation beyond this comes from the distance dependence of the irradiation intensity. So, let me show you this again. So, this intensity which we will see again later as we go in the class is proportional to r to the power 6. That means, the intensity by which it is affected, the two hydrogens are related to the distance between those two hydrogen A and B. So, you can see there is a 6th power distance. So, if I go from if 1 angstrom is going to be very strong, of course, no two hydrogens can come within 1 angstrom, they are very close, but if I have 3 to 5 and 4 angstrom, they are pretty strong. But the moment I go more than 5 angstrom, this this r to the power 6 reduces this intensity. What is this intensity? This is the intensity of the interaction, you can say, between the two protons. So, the intensity of the interaction or the intensity of how one is perturbed by the other is proportional to this, inversely proportional to the r to the power 6. So, this is a very strong dependence, which is a very short range interaction, meaning the moment you go a little bit far, the interaction energy or interaction strength decreases rapidly, and therefore, this limit of 5 to 6 angstrom comes into picture. If you go a little bit away from this, if you go to 7 or 8, there is no effect of a hydrogen which is 7 angstrom away from this hydrogen if I irradiate that. So, basically what essentially happens is, by irradiating one proton, I am able to get the information of which are the other protons present in the radius of 5 to 6 angstrom. So, that is why you see this NOESY experiment is a very useful experiment for getting distance information. This information will not be available through any of the other experiments we have seen earlier, such as 2D COSY, 2D ETOXY, which are pure J dependent, and J dependent coupling is just 3 to 4 bonds away, it is over. So, we can't go beyond 3 to 4 bonds. So, therefore, a distance, if you have two protons which are very far away in space, but very close in space, very far away in the sequence or very far away in J bond, they will not be affected in the 2D COSY and TOXY experiment. There will not be energy transfer between these two in a COSY or a TOXY, but in NOESY this will happen because of the close proximity. So, essentially this experiment therefore can be used to determine distance between two protons. How do we use this to determine distance? We will see subsequently as we go along, but this is a basic idea. So, now let us see what are the other detailed experimental schemes which are used in NOESY. So, I would recommend to you to go to this web page, this PDF, which very nicely explains in a very lucid manner how this NOE effect works. So, now let us look at the different aspects of NOESY experiment, that is how actually it is carried out. NOE as written here can be positive, negative or 0, which means suppose I irradiate one hydrogen, the second hydrogen may get enhanced in its intensity or population, it may get decreased in its intensity or population, or a third possibility it has no effect. So, no effect is basically because the two hydrogens may not be nearby, but even if they are nearby, there is a possibility that there is no effect between two hydrogens, and that is something very interesting which we will see down the line. But so the point in this case in this here is that the two hydrogens are really close, but we are not getting any NOE effect. So, what do we do in such cases? So, we will look at an alternative experiment, but otherwise generally the proton, if two protons are close in space, if I irradiate one hydrogen, the second hydrogen may either experience an increased in intensity or population, that is positive, or it may experience a decreased intensity. Now, this increase and decrease basically comes from the population difference between the energy levels. So, that is why the intensity changes. So, now this positive, negative or 0, when do we get positive enhancement, when do we get negative enhancement, or when do we get no enhancement of a signal of a proton when you irradiate a nearby proton, depends on two parameters. It depends on the spectrometer frequency at what we are operating, and that is for example 600 megahertz or 400 megahertz and so on. It depends on that, and a second factor which it depends on is the size of the molecule, that is how big is your molecule, what is the molecular weight of your sample of your molecule, and so on. So, I will this is basically the equation which is shown here, that basically NOE is either positive or negative, and it becomes 0. The NOE, as I mentioned here, it can have either positive or negative, or it can become 0. That the NOE becomes 0 when this equation is satisfied. So, you can see what is this equation. This equation now has two parameters here, as you can see, one is the frequency, that is the spectrometer frequency, and one is the tau c, which is a rotational correlation time. Rotational correlation time is a parameter which captures the size of the molecule. So, for example, if you have a molecular weight of 1000, that is 1000 Daltons, you can calculate the tau c as follows. So, I will see that a very rule of thumb which is used. So, let us say the molecular, the tau c in nanosecond is given by molecular weight in kilodalton divided by 2. So, this is a very rough estimate of a molecular weight of a correlation time. There are many assumptions in this formula. The formula assumptions are that the molecule is spherical, it is like a football, like a globular spherical shape, and it has no internal dynamics. Now, you can see, let us apply this formula. So, let us say I have a molecule which is 1000 Dalton. If I have 1000 Daltons, then my molecular weight is actually 1 kilodalton in kilo level, in a kilo units. So, when it is 1 kilodalton, the tau c is 1 divided by 2 according to this formula here, and that becomes 0.5 nanoseconds. So, when you have a molecular weight of 1 kilodalton, and your tau c in nanoseconds is 0.5, that is 0.5 nanoseconds. So, this is roughly the way to calculate tau c. Now, tau c is rotational correlation time. It basically gives you how fast the molecule is tumbling in a solution. For example, let us say a molecule is spherical like this, the molecule is actually tumbling in solution. So, how fast or how quickly there is a tumble, this is characterized by tau c. So, this is a very important number to keep in account when we are working with NOESY. So, now let us calculate this 2 pi. So, this is, you can see in this formula here, its omega is 2 pi into mu. Mu is basically the frequency, spectrometer frequency. So, if I have 400 megahertz spectrometer, I can say 400 into 10 to the power 6 into 2 pi, that is this omega, into tau c. So, tau c for 1000 we just calculated as 0.5 nanoseconds. So, I will multiply this by 10 to the power minus 9, so nanoseconds. So, now if you do this calculation, This is roughly 2 pi is 400 into 6.28, which is 2 pi into 10 to the power 6 into 0.5 into 10 raised to minus 9. This further we can calculate, this is about 1.2, if you calculate it you will get it around 1.2. So, this is coming close to 1, although it is not exactly 1, it is coming close to 1, and because of that this NOE effect, according to this rule, it says that if omega into tau c comes close to 1, your NOE effect is 0, meaning if there are 2 hydrogens which are close by, the distance may be, let us say, 4 angstrom, but if I irradiate this, it has no effect on B. Similarly, if I irradiate B, it has no effect on A. So, these two, although they are close in space, still do not interact through space by dipolar, I mean they interact through dipolar coupling, but the transfer of magnetization between A and B because of the NOE effect does not happen at this magic number, that is omega into tau c is 1. So, that, as I said, it depends on the molecular weight, which in this case we found it as 0.5, or in this case and frequency. Now, I can change the molecular weight. So, for example, if I double the molecular weight and I reduce the frequency by half, again I will get the same value. So, which means if you, it depends on these two together. So, let us say you are getting a value of 1 here, as we saw in this case, can I do something? So, the question maybe you can ask is, can I do something to still get the NOE effect? What should I do, for example, so that I can get the NOE effect even though this is turning out to be close to 1. So, one trick which you can do is that you lower the temperature. So, when you lower the temperature, the molecule, so look here, so this rotational tumbling correlation time depends on temperature, depends on the temperature. So, typically the calculation I showed you is for room temperature. So, this whole calculation here is for room temperature, but if I lower the temperature, I will start getting a higher molecular, a higher tau c, because the tumbling starts slowing down. So, because the rotation of the molecule is slowed down because of lower in temperature, it starts rotating in a slower space. So, when it starts rotating in a lower pace, its tau c basically increases, because it takes longer to rotate by the same angle compared to what it does at a higher temperature. So, as we lower the temperature, the tau c increases. Now, when the tau c increases here, let us say the 0.5 becomes 0.8 or even 1, then this number will change completely. So, by lowering the temperature, we can actually change this value. We can as well go to higher temperature. If I go to higher temperature, the tau c will decrease, because the molecule is rotating faster. So, the tau c is basically the time or it takes for the molecule to tumble by a certain degree, and that time reduces if you increase the temperature, because it is now rotating faster at a higher temperature. So, if tau c goes down, let us say from 0.5 it comes down to 0.25, then again this number will change and it will be not equal to 1 anymore. So, by changing the temperature, either increasing or decreasing, we can come out of this constraint for a given molecule for a given spectrometer. So, what we have done is, you can see here, we have not changed the molecular structure, we have not done anything to the sample, we have simply changed the temperature, either increased it or decreased it. This is one option. The second option is, suppose you cannot decrease or increase the temperature because the sample may be critically dependent on the temperature, then you can go to another spectrometer. So, instead of 400, if I go to 700 megahertz or 800 megahertz, again I am doubling the frequency here, that will double this number here, and again I will come out of this constraint of omega tau c is equal to 1. So, now I can change the spectrometer frequency as well and choose another spectrometer. So, therefore, one has a choice what one can do to get rid of this problem in particular cases. This will not normally happen in small molecules or in big proteins. Typically, this happens in the peptides. So, you see this molecular mass here is 1000, and roughly one amino acid is about 100 or 110. So, this corresponds to a peptide which is about 9 to 10 amino acids long. So, small peptides, this 9 to 10 amino acid or 9 to 12 amino acid peptides typically have this problem that you cannot do NOE experiment at room temperature with a given spectrometers like 400 or 500 megahertz, because of the problem that there is no NOE effect. So, therefore, we have to overcome that. So, let us say that I cannot change the temperature beyond certain range, and let us say that I cannot even change the spectrometer, I have only one spectrometer in my lab, then what do I do? Then for that you will have to go to another experiment, an alternative to NOESY called ROSY, which we will see later after this NOE experiment, but that is another alternative which we can use if you cannot do NOE because of this constraint. Now, coming to this point here, that the maximum enhancement, meaning how much can the signal be increased by irradiating one nucleus is about 50%, you cannot go beyond this, this is a theoretical limit. And similarly, how much can it go down if I irradiate one nucleus, the second reduces in intensity, and that can be 100%. That means, by it can completely go down by 100% if there is a negative NOE. So, you see negative and positive NOE are possible only when this constraint is not there. So, typically the positive NOE is when omega into tau c is much less than 1, we have positive enhancement, omega into tau c is much greater than 1, we have negative enhancement. So, this positive and negative depends on these two parameters as we already discussed. In this is typically happens in the case of proteins, because in proteins we have very high tau c, the tau c value is typically of the order of 10 to 20 nanoseconds, and omega we typically work, omega is 700 to 800 megahertz, this is for proteins. So, therefore, if you combine the two parameters, you will see that this number is much higher than 1, and therefore, we are in the negative enhancement regime when it comes to biomolecules. But very small molecules where the omega into tau c is much less than 1, so there it will be positive enhancement. But this is essentially the traditional 1D NOE experiment which is to be done earlier, which is no longer done today. What is done is a 2D NOESY experiment, not a 1D experiment. So, in a 2D NOESY experiment, as we will see now, we do not irradiate a particular proton. We do not irradiate as using a continuous RF, as I was explaining in the previous slide. We use a simple 2D pulse sequence, which is shown here for recording the data. So, this is a standard 3 pulse experiment for 2D NOESY, and it is nowadays used for every molecule including biomolecules. So, it is very important to understand this experiment now, how it works, and then what is the information, how is the information that we get is analyzed. So, let us start from this experiment first. So, the first pulse is always, as any 2D experiment, an excitation pulse. So, we excite the spin, a particular spin A, we bring it to the transverse plane. So, this is what is shown here, we have brought it to the transverse plane by applying a 90-degree pulse. Now, during this period, which is labeled as T1, the spin starts precessing around the magnetic field. So, look at this picture here, it starts precessing in the xy plane around the z axis, because z axis is our main magnetic field, it starts precessing around that. So, this is similar to what we have been seeing in the case of 2D COSY and 2D TOCSY. During that period, now because it is evolving with a frequency omega A, its FID is written like this, because this is like an FID now in the T1. Although we are not detecting it, this is an indirect dimension of a 2D experiment. So, we are not physically detecting it, the physical actual detection takes place here in this part, the second FID, but in the first FID we do not do that. So, in the first, so this is basically cosine omega T1. Now, after some time when it has not completely decayed, although we are showing a signal decaying to 0, please keep in mind that we do not wait till this happens, we only wait for a few points here, and that is how much is the number of experiments done. It is not that like shown here that you have to wait till the FID is 0, then you apply the second pulse. It is just schematically shown here that you apply the pulse, you wait for a duration and then apply the second pulse. So, when you apply the second pulse, this magnetization goes to minus z or plus z depending on the phase of this pulse. Now, during this portion of the time from here to here, you see this part of the sequence, there is just a simple mixing time, meaning there is nothing happening here, it is just an evolution, it is not even evolution, this is not like a T1, because T1 is something which varies with time, as we saw in the previous class how a 2D is conducted experiment. Here it is a fixed time, a fixed duration. So, that means this particular time the spin now starts going back towards z axis. Now, when it goes from minus z to plus z, it is pure T1 relaxation, there is no T2 here. Why? Because we are not in the xy plane. So, if you recollect our slides on T1 and T2, T2 is basically something which happens in the xy plane, that is a dephasing of the magnetization, whereas T1 is something which happens along the z axis and it is the magnetization recovery along the z plane or z axis. So, that what happens in this particular case, this magnetization which is minus z starts coming slowly towards this plus z. During that period of time, it starts now affecting the other spin, because two spins A and B, if they are coupled to each other by dipolar coupling, and if we are not in that condition that omega into tau c is equal to 1, where it is 0 NO effect, let us say we are not in that condition. So, if you are away from that condition, the two spins A and B can start now transferring magnetization to each other, and that polarization transfer is what is called NOE, and polarization meaning population transfer. That means the population of spin B between alpha state and the beta state is affected because of the relaxation of A. So, this effect, now this changes the intensity of B, and now the B population, when you apply the second pulse, the B is now excited and it starts evolving. So, what happens is that the intensity of B which we excite here by this pulse is dependent on how much of the A and B magnetization had been exchanged. So, that is during this mixing period. So, during this mixing period, when A and B exchange the magnetization, the B's magnetization which gets excited now is not the original B magnetization, it is something depending on how much A magnetization has come to B, and that carries the information of the frequency of A as well, because before applying this mixing pulse we saw that we had an evolution period. So, during this period the frequency of A was labeled or captured. Now, that frequency affects the intensity of A, and the intensity of A affects intensity of B, and therefore, the intensity of B carries the effect of the frequency of A information. That is how these two gets coupled to each other, meaning they are joined to each other in frequency, because the intensity, the modulation of intensity of A is transferred to the intensity of B. Now, when the B is excited, it gets excited and it starts evolving like any other spin, and that is captured by physically, and that is called that FID, free induction decay, during this period. This is called T2 period, a second time evolution period which is shown here. So, that is cosine omega B into T2. So, therefore, omega A into T1 is now multiplied with omega B into T2, and that is the combined FID that we will get in a 2D NOE experiment. So, the important point here is this mixing time. If the mixing time is 0, let us say we do not have any mixing time, then there is no time for the A spin magnetization to go to B. So, therefore, it will not have any effect on B, and the B's magnetization will be its original magnetization. But because of this effect that A spin is now transferring its polarization to B, the B's effect is now dependent on this time. So, the longer the time you give, the higher is the transfer, but there is again a limit to how long you can give. You cannot give for a very long duration. This depends on the T1 of the sample. So, if the T1 of this proton of B and A are very short, the T1 value, we are talking about relaxation T1, longitudinal relaxation, then you can't go beyond that time period for the mixing time. So, what is the typical value that we use for proteins? For biomolecules we use about 60 to 80 milliseconds, and we do not use more than that, and there are some other side effects which happens if you go beyond 80 or 100 or about 120 in proteins, which we will see when we analyze this NOESY for structure determination, and there we will see that there is effect called spin diffusion. Spin diffusion is basically a transfer of magnetization from A to B to C, and C and A may not be close to each other, but because B was as an intermediate spin, it affects the it thinks the magnetization has gone from A to C, and actually which is not the real scenario. Actually it should have stopped at B, but this further transfer to C happens because we give a very long mixing time. So, the mixing time has to be appropriately chosen, so that we only capture the magnetization transfer or polarization transfer between two very close or closely spaced nucleus. Okay. So, we will now see in the next class how this pulse sequence translates into the spectrum, what kind of a spectral pattern we will expect to see having now transferred the polarization from A to B. We will analyze that in the next class.